Assalamualaikum and good day everyone. So today I'm going to continue on our chapter 2, okay, and our chapter 2 part 2, okay, application of Fourier series in electrical circuits, okay. So let me share my screen, okay. Okay, so chapter 2 part 2. So the part that we have yet to cover is this, okay? So Fourier series application in circuits. So when we refer to circuits, we have three main elements that we will cover, okay? Which is the resistor, the inductor, and the capacitor, okay? So I will speak more on the resistor, and hopefully you will able to relate similarly to inductor and capacitor, okay? Here, in capacitor circuits, okay, in capacitor circuits you have this is as the source, voltage source, okay, in dependent of time because there is element of time here, okay. And then you can see xc is the reactance, reactance which is 1 over j omega c, okay, 1 over j omega c. So this one you can regard just like an impedance, okay. Impedance is let me take the the pen, okay. So you know resistance, right? Resistance is your r, okay. This is a real number, okay. And then you have actually some kinds like resistance, but we call it in reactance, for the inductance or capacitance, okay. So you have x jx here, okay. And then you have this as a impedance, okay, just like the total resistance, which consists of the real part, which is the resistor, and the imaginary part of reactance due to the capacitor or inductor, okay. So this is resistance for real part or resistor, this one is the imaginary parts, okay. So and then you can see here, okay, for the capacitors, okay, for the capacitors xc, okay, it is 1 j omega c, am I correct? And if you want to bring this j upward, it will be negative j, okay, it will be negative j, okay. Okay, sorry, it will be like this, okay. So for example, this one may consist of um, the capacitor, and this one is may consist of your due to reactance due to your inductance, okay. So for the capacitor case, so vt, okay, the same, okay, just like in the normal circuits that you learned before, I mean not in normal circuit, in the maybe in circuit theory, v equals to ir, okay, but that one is for resistance. How about reactance? You will have I, the same current, okay, the same, just a bit modification to the formula, then this one is your reactance due to capacitance, okay. The normal one that you learn in your circuit theory is like this, right? I think maybe in your secondary school even, okay, this one is normal, Ohm's law, okay. Similarly, for the inductor circuit, so but it's a bit different. You have XL for the reactance due to inductor is J omega L. Okay, J omega L. And to know the reactance due, to know this one is the reactance due to capacitance. You want to relate to the voltage equation. Similarly, like the reactance due to capacitance, now you have reactance due to inductor to be input in this V equation, voltage equation, and you're going to have like this. Okay. Then this is the resistor circuits. Okay, resistor circuit VT, IT, and R. Okay, this one is straightforward. So in circuits, okay, in circuits, this is your series circuit. Okay, Z, which I shown just now, right? The impedance is equal to R plus reactance due to inductor. So R plus J omega L. So VZ, VT equals to I T Z. Z is impedance, the total impedance. Okay. If we go to this one, okay, series circuits containing resistor and capacitor, you have Z equals to R plus XC. Okay, just like what I shown just now. V T I T Z. So how about parallel circuits? Parallel circuits, how is it? So it is just the same. Okay, means that this one will be treated just like impedance, just like resistance. Okay, but this one we call it is as a reactance. Okay, so for the parallel circuits, for example, I think you should guys should know this rule before. I mean, you learn from circuit theory, the parallel circuits. Okay, how is it? Okay, so if it's for the parallel circuit, for this case of containing reactance, for example, okay, how we would like to see the impedance. Okay, impedance or the parallel. If this is plus, if this is R plus XL is plus, then how about the in terms of the reactance, in terms of uh, parallel circuit? Okay, the normal that you have 1 over R. Okay, 1 over R equivalent. Okay, this is what you understand from your what we call is from your normal resistance equation. So you have 1R1 and so on. Let's say the circuit having two resistor in series, in parallel. Okay, in parallel. Okay. Oh, sorry. Okay, in parallel. Okay, this one is in case if it's resistor. How about we doesn't know what is that we are given as Z. Okay, we given as Z. Okay, so Z1 and Z2. Okay, Z1 and Z2. This one, this is Z2. Okay, so 1 over 1, this is 1 over Z. Okay, equivalent over 1 over Z equivalent is Z1. Okay, Z1 plus, sorry, it's a bit difficult using this. I hope you guys can still see my handwriting, over Z2. Okay, so which Z is actually can have this the combination, or maybe have standalone, maybe this one is XL inside or R inside or XC inside. Okay, but okay, this is how you read it. Okay, this one is the basic equation that you learn. This one, if this is impedance. Okay, we why we call about it impedance, because it may have the imaginary part or reactance. Reactance. Okay, So now we go to these examples. Okay, we go for this example R circuits. Okay, before we actually go to this what we call is this one, we need to refresh a bit. Okay, we need to refresh a bit from the previous lecture. Okay, which is for here. It is chapter 2 part 1. Chapter 2 part 1. Okay, Fs Fourier series symmetrical properties. Okay, so given this is your frequency spectrum. Okay, frequency spectrum. Okay, Fs should be represented by Vt a naught over 2 sigma from 1 summation from 1 to infinity an cos n omega naught t theta n. This one is for single-sided spectrum. Okay, single-sided spectrum means that it can be double-sided later on whatsoever. But if it's involved double-sided, it is a exponential, right? So this one, okay, have to take note. This one is the general equation for single-sided. So you have n naught over 2. Okay, which one is this one is actually at n equals to 0, right? Okay, this one is normally DC component, direct current, so no phase. And then where in theta is actually inverse tangent of negative Bn over A, then you have An equals to An square plus Bn square in this one. And this is Fourier coefficient can be obtained by integration. Okay, so n naught 2 over t, t over 0, Vt dt, and this one. Okay, 2 over t, Vt cos n omega naught t dt, and 2t t0 Vt sine omega naught t dt. Okay, so remember there is t inside. T dt, t dt, and this one is Vt only. Okay. So if we want to see first, okay, Fs symmetrical property, A0 is merely time average of Vt. It is 0 if it's symmetry in the period. So if we get a signal, okay, if it's symmetry automatically, if it's symmetry at the period of time t over the horizontal, so A0 will be directly 0. Okay, this one will be directly 0. uh, if it's a cosine, like if it's cosine, so it is even symmetry, then Bn will be 0. Okay, Bn will be 0 here. Bn will be 0. Okay, Fourier coefficient Bn will be 0. Okay, if you see this one is combined Fourier series. Okay, combined Fourier series mean you actually your real term should consist of sine. Okay, I mean the initial should consist an cos or n omega naught t, b sine n omega naught t. Okay, but when we this combine, we only have cos component, right? Okay, so if it's even symmetry, your bn will be 0. If it's like cosine like symmetry, means cosine like symmetry means it is symmetry like even symmetry. Okay, okay, so if it's this is the case, if this is case, your bn will be 0. Okay, bn will be 0. So here your bn will be 0. So if anything, if it 0 means time by with 0 will result in 0, right? So if that is the case, for case that having symmetric over time exists, and also and cosine like symmetry, so bn will be 0. So only left you with only left you with an. Okay, only left you at an. Okay, the next case, if you have sign like odd symmetry. Okay, odd sign like odd symmetry. If you have sign like odd symmetry, okay, which is this one is positive, this one is negative. So what happened is that your an will be 0 in this case. Okay, and your an will be 0. So if you have equation like this, means some wave like this, signal like this, so it is symmetry, so means that your A0 will be 0. Okay, A0 will be 0, and at the same time AN will be 0. So you will only left, okay, you will only left with BN. Okay, and then the next, AN equals to BN equals to 0 for all even value. For all even value means N, 2, and 4, and 6. Okay, except A naught here, except A naught, okay, means your N2, N4, N6, N8, and so on, okay, is equals to 0 for all even value except your A naught. Okay, if VT has skew rotational symmetry. Okay, you know how the skew look like, right? Okay, refer to the previous lecture how the skew signal look like. I just want to show you so that you always need to refer to your lecture note. Okay, skew. I think it's chapter 1, part 1. Not sure. Okay, how the skew signal look like? Okay, chapter 1, part 1. Okay, this is skew signal. Okay, so this is skew signal. So for skew signal, AN, BN equals to 0 for all even value. For N, 2, 4, 6, and so on, except A naught. Okay, so this is the we recall before we proceed to the next to chapter 2, part 2. This one is from chapter 2, part 1. Okay, we go to chapter 2, part 2, continue. Okay, so here, given that VT is an odd symmetry, you see this signal, you see first this signal, you see this is actually what symmetric? Is it even or is it odd? So if you see here, is actually is odd symmetry. Odd symmetry means it look like sign-like symmetry. Okay, so what happened when sign-like symmetry? AN is equals to 0. Okay, AN equals to 0. AN equals to 0. Okay, AN is equal to 0. So you don't have this element AN. Okay, it is equals to 0. The next is what? And it is symmetry. So A naught is equals to 0. So, okay. So your equation is that first is sign like symmetry, AN 0 and A naught is 0. So this one is 0, this one is 0. So you only left with BN actually. Okay, and refer to the appendix. Okay, refer to the appendix. Okay, so this is the Fourier series. I mean the appendix you refer. So this is the equation that we see. Okay, so A naught is equals to 0 already, and AN is equals to 0 already. Okay, so we only left with BN. Okay, we only left with BN. So this is the Fourier coefficients. Okay, this one is 0 already. This one is 0. So we left with this B2 over T and so on. Okay. So this is the things that the comments. AN equals 0 for odd, BN equals to 0 for even. This is just like a more brief comments. Like what in the slide. Okay. This. Okay. And AN, BN 0 for n even. Okay, so A 0 over 2 for average value of FT. This one is 0 if your signal is symmetrical. Okay, symmetrical. So now let me try knowing this and seeing this. Okay, how we actually going to solve this equation? How actually we going to solve this equation? So I'm changing the screen. So you please refer to this lectures note while you see, because I'm going to use my screen and totally uh, on the pane. Okay, means I will not show the question. Okay, because I need to demonstrate how to actually solve them. Okay, and hopefully it's still clear to you guys. Okay. um, okay, so now we go to the pain. Okay. Okay, wait. I see my mouse. Okay, here. Okay, new, don't save. Okay. Wait for a while. I get my charger. Okay. So now we are going to solve this equation, right? Okay. First, we have the wave. I don't draw all the wave look like. Okay. I just show the repeated parts. Okay. So if you see that the wave is like this. Okay. Okay. So you can see this one is in in millivolts. Okay. In millivolt. So what is the maximum value? Is 10 millivolt. Okay. 10 millivolt. Okay. um, 10 millivolt. Okay, and then you can see the complete period. Okay, the complete period, if you have another here, it is 2 milliseconds. Okay, so you know that you're referring to to the bn. Okay, to the given bn. Okay, bn, this one you get from your you can get it from your appendix. What is your bn? Okay, so then you have 4n, 4 over t. Okay, 4 over t, integration from 0. Okay, integration from 0, and from the t of half. Okay, from the t of half, half of your complete period. And then you have your function. Okay, you have a function. In this case, is vt. Okay, in this case is vt, because in the appendix it's just show the general look like the general function. Okay, general function. This, if this is ft, it can be anything. For this case, for our case, the ft is the voltage. The signal given is a voltage. Okay, so bn from 0 until t over 2, and then you have the function, which in this our case, is our vt. Okay, this is our vt, which is the amplitude. The amplitude. So let's say we just put here first as an a. Okay, for easy calculation, you put an a first, and then you have your sine n omega t dt. Okay. I hope it's clear there. Okay. Okay, I think it's clear. Okay. Okay. So this is your sine. This is your sine. Okay, and then you need to do the, do the starting of the integration, bn 4 over t, t over 2, this one. Okay, and then what is for this equation, just you can put here first, the complete period is what? T is equal to 2 millisecond. Am I correct? And then for your amplitude, okay, for your amplitude, oh my god, my battery. Okay, never mind. Okay, so then you continue, okay, to solve this integration, so what is t over 2 here? It's actually 4 over t, okay, integration 0 t over 2. You have t over 2 is 2 millisecond, right? So is t over 2 is 2, t over 2 is actually 2 millisecond divided by 2. So you have 1 millisecond, okay? So here is actually 1 millisecond, okay? And then you have your A amplitude, you can put it later on, okay? You can put it later on, A sine omega t dt, okay? And then you uh, expand the signal, okay, for, or expand the integration for over t, okay? You do the integration part inside, you do the integration part inside, okay, for okay, and then from here actually you can also refer to your appendix, how to integrate, so don't need to memorize so much, okay, for this one. Okay, this one I suggest you guys to memorize, this one. However, the things like the mathematical, you don't need to memorize. Okay, you can see here, integration of sine you get 1, integration of cos you get 1, and remember the sign, okay, this one there is negative here, okay, so refer to appendix, means you will know what you should remember and what you should, okay, but this one I suggest you to remember, this characteristic, so easy for you to solve the question a bit faster. Okay, where were we just now? Okay, so when we want to integrate, our sign, okay, it will result in a cos, okay, in a cos. So cos is what just now, integration of sine. We will have okay, this one, when we want to integrate the sine, okay, we will have what we call, this is sine omega t dt, and I forget, there is sine n, there is sine, okay, there is sine n, inside n omega naught, sorry, n. So when we want to integrate, when we want to integrate cos, we will get sine, okay. So a, I need to refer again to the appendix, okay, a over, okay, nw, okay, cos n omega naught t, okay. This is when you want to integrate the sine, you get the cos, okay, sine you get the cos. Okay. Um, then you have your A. Okay. Sorry. Then this one is actually, this is 0 until 1m. 0 until 1m. Okay. Then you divide it further. Okay, and you divide it further to get the complete one. Okay. Integrations. Okay. Integrations of negative 1, 0. Okay. Negative 1 to 0, the time, negative 1 to 0, which is here is 1 milli, 1 milli. And then A sign. Okay. Because it is negative, A sign. Okay. Sorry, what, where, I think, okay, sorry, this one. Okay, and then you have your A sign. Okay. A sign n omega. Okay. T dt. Okay. And then plus with, if this is 0, so it's the 0 is here. Okay. Like this. And then you have 1 milli. Okay. Remember it's milli, because it's time in half. It's actually 2 divided by 2 is 1 milli. Okay. The an sine n omega t dt. Okay. Close your bracket. Okay. Then okay. The next is actually you expand the integration to get the to do the integration, you get the cos. So 4, okay, 4 over t. Okay. Integrate sign, you will get the integrate the sign, you will get the negative. You get the negative cos. Okay. Integrate the sign. Sorry, integrate the sign, you get negative cos. Okay. Correct. Okay. Then later on 4 over t. 4 over t you integrate. Okay. Then you get like this. Okay. And then you have a and omega. Okay. Everything inside, when you integrate it from sign like this, everything inside is put outside the n omega. T is not. We don't put here, we only put everything inside. Okay. N omega. Okay. Here depends on the equation. So n omega cos n omega t. Okay. And the limit is from negative 1 milli, okay, to 0. Okay. And next, its friend. Okay. The friend here. Okay. Negative a and omega. Then you have the cos here. Okay. Cos and n omega t. Close, and we see the limit as 0, from 0 to 1. Then we close the integrations. Okay. Next, you open these limits. Open these limits. So you have here still 4 over t. Okay. It's a bit difficult to use this. If there is a whiteboard, it's easier. Okay. Then this one you just put inside. You just put inside. Okay. A n w n omega. So okay. What cos zero? Cos zero is what? Where's my calculator? Cos zero is 1, right? But let me get my calculator. Okay. So you have it's 1 here. Okay. You have 1 here. Because it's cos 1, right? And then the next is negative 1 milli. Okay. Negative 1 milli. So if you put negative 1 and you put milli, okay, you have cos negative and omega. Okay, what is the omega? What is the omega? So omega here, okay, since you know that your t is 2 millisecond, okay, so what is actually your omega? Okay, omega is actually 2 pi f, which is 2 pi over t, right? So your t here is 2 milliseconds, okay? So it's 2 pi over 2 millisecond, which is equal to how much? So it is 100, okay? Sorry, it's 1000. So your omega is 1000, okay? 1000 pi, okay? So then proceed just now. So 1 minus cos, 1 minus cos, we have cos omega is 1000 pi, and for n equals to 1, okay, for n equals to 1, because later on we will have 1 2 3 and so on, 1 2 3 and so on. Okay, so cos n, okay, this one is we settle for the first, for example 1, later we have 3 and so on, one, I mean n1 and 3, n1 and 2 and 3 and so on. Okay, where were we? Cos, so you have 1000. Okay, this is to get your bn. Remember, this is to get your bn. Okay, 1 minus cos negative, because you have negative. Okay, negative 1 milli, am I correct? Negative 1 milli, and then times, okay, t, and omega is 1000 pi, okay, and then your n is and your n, you put just like your n, means you just put your n here, okay, just put n times n, okay. So if you see 1 milli times 1000, you get what? It's 1, right? 1 milli times 1000, you get 1, okay. So this one is actually 1, only 1, and then plus with minus here, okay, plus minus a and omega, okay, for this portion. Now we have cos, cos 1 milli, this 1 milli, 1 milli, cos 1 milli. So again, I think it's almost similar. So that's why you can just use cos n pi, okay, almost similar to this, okay. And then 0, whatever minus 0 means you will have like minus of 1. Okay, like minus of 1, because cos 0, right? Then you close the integration. Okay, you close the integrations. So if you see this one and this one is minus minus positive, right? Minus minus will be positive. Okay, so next, here you bring out the a, you bring out the a. Okay, you bring out the a, because all of them is having the a and w, right? So for a is what? A is actually your amplitude, which is 10 millivolt, but we can put here first 10a. Sorry, 10a, and t and omega. Okay, you put outside, and then the integration, and then inside the limits, inside the brackets. Okay, I'm doing it a bit slow so that hopefully you guys can see the progress, but later on when you expert, you can do it very fast, inshallah. Okay, then after that you have 1 minus. Okay, then you have 1 minus cos, f1 minus cos. Inside here is a negative, right? Negative n pi. Okay, and then you have plus minus here is minus here. Okay, minus. Then you have cos. Okay, you have cos n pi, n pi. Okay, and then this one is minus just now, right? Minus minus is become 1. Okay, and then close brackets. Okay, you know that, okay, from mathematics you know that cos n in pi equals to cos negative n pi. Okay, just like, for example, you can put inside your calculator. For example, you just try cos negative 90. Okay, cos negative 90 is 0. Also the same as cos 90, okay, which is 0. So this is the properties of cos. So because of this, they are minus minus, they are like the total. They are like the total. Okay, and they are the same. Okay, so you have 1 plus 1 here. Okay, 1 plus 1, you have 2. Okay, then this one, because they are the same, they are the same, so you can just cos n pi. Okay, and don't forget the 2. Okay, because it's like a addition of both. Okay, because they are the same. And then you put the 4a. Okay, 4a here, and then what is the amplitude? Okay, the amplitude is 10 millivolt. Okay, okay, but here t and omega. Okay, and then where is the space? Okay, then 4a, for amplitude here is but we can, in this case we can put the amplitude directly, because it's, we already know the amplitude is what is the amplitude? 10 millivolt. 10 millivolt. Okay, over the period. Okay, the period is what just now, the period is 2 milli. Okay, 2 milli, and n we don't know. Not that we don't know, it will replace n 1 2 3 4 5 and so on. Okay, so 2 m. Okay, 2 millisecond, and your n and your omega. Okay, if you see this side, they can be this one can be potong, can be cancelled out, and then this one can cancel out, the result in 2. Okay, and then you have sorry, I need to check. And okay, sine A. Okay, okay, this one maybe we don't need to replace first. Okay, wait, when I'm confused with my own writing, it's too terrible to even read my own writing at this time. Okay, okay, if you see now, I'm bringing up. Okay, so this is 2, 2 minus 2 cos whatever is that. Okay, whatever is there, you can bring it out. Okay, you can bring it out. um 2. Okay, for a. Okay, you bring out the 2, you bring out the 2, and your t is 2 milli, right? 2 milli. Okay, this is simplified, and then you have your n, and this is your omega. You bring out the 2, so you only left with 1 over cos. Okay, cos n pi. Okay, then you make it simplification. Okay, so you have 4. Okay, you have 4, you have 10 milli, then you have 2 milli. N is we going to substitute one by one, like n 1 2 3. Let's say question 1 until how many harmonics. So you will have this, you're going to use this n to be substitute, so don't change the n here. And omega, so y minus cos n theta. Okay, so you see here. Okay, you can cancel out this one and this one. Okay, the 2 still here. Okay, and then this one will cancel out with this one, so you will live with 40. So you will live with 40. Okay, over n omega. Okay, you left with this, the n omega. So what is your omega? Sorry, I think, wait, is there anything that I left out? Omega. Okay, so, and then I think, please recheck. I hopefully that there is nothing left out, because it's still quite difficult to write using using this. And then so in the end, you will have 4a. Okay, so here for me it's depend. You can substitute, or you cannot substitute. I mean, you can decide to substitute, or you can decide not to substitute. Okay, you can decide not to substitute. So then you have 4a. Okay, 4a. over pi n. Okay, over pi n. Okay, you see your omega just now, omega is 1000 pi. Okay, this is your omega 1000 pi. Where were we? Okay. You have 4a over pi n, which is, then you have still here 1 minus cos n pi. Okay. So here, your pi is actually what just now? 1000. Your omega is 1000 pi. Okay. Your omega is actually 1000 pi. Okay. Then you have 4a, the amplitude. Okay. Then omega. Okay. And then you have pi and n. 1 minus cos n pi. Okay. Let me check first. Hopefully I didn't make any mistake. Okay. To cancel out. And actually this one, maybe it is wise to not to change first, because amplitude can change. Okay, we can change the amplitude. So they say this one is, we just put it at A. Can just put this as A, and then your omega. Okay, omega is 2 pi f over 2 pi. Okay, so it's 1000 pi. Okay, n is will be changed. Okay, this one is will be cut. Okay, this one will be cut. So here, okay, this portion, okay, this portion, I do it here. I do it here. Okay, so if you see this one, 2 is cancelled out with this 2. Okay, then you have m and omega here. So you have 1 milli times your omega. Your omega is just now is 1000, 1000 pi. Okay, so that's why it's become only pi. Okay, it's become only 5. So that's why you have pi here. Okay, and then the n is not changed, and then you have 4a. Okay, so this is the your bn. Okay, and your bn, and then you get your bn. I continue here. Sorry for the mess. Okay, so now you have your bn. Okay, so your bn, which is, you put inside, look like this. Okay, so you have option 0, and you have option like 4 pi, 4a, 4a over pi n. Okay, and then if you see the question, okay, this one is okay, if you see the question, where's the question? Sorry. Okay, if you see the question, this one is what symmetry? This one is sign symmetry, right? Sign like symmetry. Okay, what happened to sign like symmetry? In the appendix, okay, go to the appendix. Okay, for even number, okay, for even number, it is 0 bn. So bn1, bn2, bn4, bn6 is 0, but it is not 0 for the odd number, b1, b3, b5. Okay, so okay, okay, and because I'm doing, okay, okay, so this, so here is 0 for even numbers. For even numbers, 2, 4, and the rest, which is even numbers. And it is not even, is not zero for odd numbers, so 1, 3, and so on, odd numbers. Okay, so now you have your bn. So your vt, okay, your vt just now, okay, your vt now, okay, you have your bn. Okay, you see your appendix, again, you need to see your appendix. Okay, you see your appendix. So from here, okay, then we continue. We see appendix, continue. Then you see for your VT, okay, you see for your VT. So your VT actually VT, okay. What is the question? Your VT is 40 pi. Okay, this one is at 1, 1, and then you have sine. Then omega is 1000 pi t, okay, and then you have 40, and n equals to 3, right? N equals to 3, because you, for even number is 0, 3 pi, no space, wait, okay, it is plus 40 over 3 pi, okay, 40 over 3 pi, sine 3000, because now it's 3, 3000 pi t, and so on, and so on, 5, 7, okay, and it is in terms of millivolt, okay, it is in terms of millivolt. And then how we're going to obtain our I, okay, our I is simply IT equals to your VT over R, okay. R, you already know for this question, R is 10 ohm, so you just divide all of this with 10, with 10 ohm, so you will left with 40 10 pi sine 1000 t, 1000 pi t, and so on, okay, and so on, because this one is repeated, for this one is for n1 and n3, okay. So please refer to the slide for the complete answer for slide, example for R circuits. Okay, I'm going to to, how can I, okay, save, okay, save, I will put later on, uh, some, okay, okay, so, wait, okay, okay, now we go to the next, we go to the next. Okay, just now is you to obtain the BN. Okay, so your BN is actually your 0 for n over pi n, and then relate you how you're going to have your VT. Okay, how you have your VT, and then how you're going to have your I. Okay, okay. So next, what is next? Okay, this one. So we have the example of R circuits. Okay, to actually obtain this R. Okay, and then you have these L circuits. Okay, you have this which is the inductor circuits. So inductor circuits, okay, you have to know what is the difference. If this is L, okay, I mean different with the resistance and capacitance. For the L circuits, you have XL, J omega L, okay, and then omega L, 90 degrees, okay, 90 degrees. Okay, and then because you see how we actually have this J, go back to your Euler's theorem, okay, that I teach you guys, okay, and how actually, at what angle actually we will have this J. Okay, at what angle we have this J equals to 90. I mean, at what angle giving us J. Okay, so it is 90, sine 90, J sine 90, cos 90 is 0 plus J sine 90, we will end up at 90 degrees. Okay, so this is how we're going to, if we want to make this disappear. Okay, and then omega 1 1000 pi, 3000 pi, and so on. Okay, this is almost a similar case with the previous examples. The signals are the same now. The signals still the same, but we replace the R with our L. Okay, so you see now we have 90 degree here. Okay, we have 90 degree. So 90 degree means the phase addition phase, whether it's delay or one. Okay, there is phase different with of 90 degree. So you have, so you solve for this. Okay, for this one. Okay, for this, not sure if you can see the cursor, my cursor. Okay, not sure you can see it, or I think you cannot see it. Okay, I'm not sure you can see or not. Okay, this one. Okay, if you see, not sure you guys can see. I mean, not sure you can see my cursor or not. Oh, okay, I'm not sure you can see. Okay, never mind. Okay, okay. Oh, okay, you can see. You can see. Okay. So if you can see here, this is, where were we? Okay. So refer to your, okay, you see here, this is the previous, sine pi. Okay, you see there is no, because it's a resistor, purely resistor, so you don't have any phase difference. Okay, then for the L circuits, okay, for the L circuits, you have like this. Okay, so you have to add 90 degree, okay, which is minus 90 degree, minus 90 degree. This, because this is 90 degree, right? Okay, minus 90 degree. Okay, because this question relate to your R, I mean to the previous example, so no need to start from scratch. Okay, but you need to start from scratch if your question is given L, okay, given L or given C. Yeah, okay. um, so how you actually have, okay, how you actually have this pi square. Okay, you need to know how you actually have this pi square. Okay, because this is your VT. Okay, this is your VT. Okay, maybe I will show. Where's the pen? Okay, go to the pen. New pen. Wait. Okay, so because you have IT, okay, you have IT equals to VT over your X. Okay, XL. Okay, your XL is now is what just now is sorry, okay, see my too many screens. I don't know which one to refer to, because okay. So J omega L, so this one is you have omega L. Okay, you have omega L. Okay, L is 0.1 Henry. Okay, L is 0.1 Henry. So XL, okay, XL is J omega L, right? J omega L. Okay, and then omega J is actually 1000, right? 1000 pi, I think. Okay, and then because it's the same like the previous equation. Okay, and your L is 0.1 Henry. Okay, so 1000 pi over 0. Times 0.1. Okay, times 0.1 is actually J 100 pi. Okay, 100 pi. Correct me if I'm wrong. And then J, if you want to make it to be, you use like Euler's theorem. Okay, so this is actually 90 degree. Okay, so you see there is another pi here. Okay, so that's why your VT just now, okay, your VT, which is consists of 40, for example, 40 pi sine 1000 pi t, and so on, because it's continuous, divide by, okay, divide by 100 pi. So you see pi here and pi here. That's why you have the resultant 40, 100 pi square. Okay, and so on. Okay, so that's why you have pi square here. Okay, pi square. Okay. Similarly, for containing the capacitance, okay, capacitance, you see J here, right? If you want to carry upward, it will be negative J. So negative J means negative 90 degree. Okay. How you get this? I leave it to you guys. Okay, it's just like repetition. You guys need to know until now how you get it, to get it negative 90. So the next, if we're going to have combinations, okay, of circuits, okay, R and L circuits. If we have this combination, you need to combine them. Okay, for example, what is this? RNA circuit. So just like what I told you just now, um, for example, the difficult using screen. If I'm not using screen, I have to record using phone. If I record using phone, I have memory problem just like semester, because if I record 1 hour, then finish my memory, my phone memory. Where was I? So Z, just like I told you guys, AZR plus J. This is the full complete, consists of J JXC, capacitance, reactant due to capacitance, and reactant due to inductance. And this is what we call as impedance. Okay, this one is resistance. Okay. So this question, um, determine the Fs of the current. Okay, the current. So you have this is 0.1, this is your 200, and given this is your Vt. Okay, this is your Vt. So here, where's your Vt? So Vt, how you get your Vt? Okay, 40 sine 1000, 40 pi. This one is from the previous example. Then I over Vt over Z. Z is because it's a total impedance containing the resistance and inductance. So you solve this one and you get the Z. Z, you see, just like how I teach you guys just now. Okay, how I taught you guys this one, and before this, even before this slide. Okay, I shown just now, right? And then you get the omega 1, omega 3, and omega 5, and you make sum. Okay, let's say question until fifth harmonics. So you solve accordingly. Okay, I equals to V1 Z1 V2 Z2 V3 Z3 and so on. Okay, and so on. But this one, because for even it is 0, for even it is 0. Okay, if we refer to the previous question. Okay, so 1, 3, 5, and so on. Okay, 1, 3, 5, so on. You see here 1000 pi t, 3000 pi t, 5000 pi t. Okay, and then you have your I of Vt over Z, 40 pi over your Z. So your Z is actually, you need to solve first your Z, which is j omega L. J omega L, this one. Okay, you put this one is not related because it's capacitance. So it is 0. Okay, and you have your R, and then you have J, and what is for capacity, for inductance is omega A, right? So that's why you need to solve this first. Okay, and then you get this equation. Okay, try to do this at your own leisure time. Okay, and then what else? Okay, so this is the table. So this is the table. Okay, so try this and try to solve the tutorial. Okay, so with that we finish this chapter 2 part 2 continuous for Fourier series application in circuits. If there is any mistake or anything that maybe some mistake in my solving or whatsoever, okay, because I'm doing this hands on. Okay, maybe some mistake or things that, so let me know. Okay, so with that we finish our lecture. Okay, see you guys in the next lecture.